Sawadee, and welcome to Module 7, Statistical Analysis, Topic 7.5, Data Visualization. By the end of Topic 7.5, you should be able to choose the appropriate graphical display for each type of data, perform basic data display commands in Stata, including graphical summaries of variables and graphical comparisons, and be aware of other options for creating visualizations of data. You can create the graphs in this topic using the Stata do file, Module 7, Topic 7.5, Stata example syntax, and the Mix 2017 10% random sample data. Why is data presentation and visualization important? There's a story behind every data set, and your job is to tell the story as accurately as possible. Some data sets are simple, such as one that might only have weight and height, which are two measures that are universally understood. Some data sets are very complex, like relational or network data. The concepts can be challenging to communicate. One of the best ways we can communicate our story and make data accessible is through data presentation. The essential function of data presentation is to look at your data. It's the first step in any data analysis. When we really understand our data and learn to communicate it, this can become a very powerful tool. We can use graphs and/or summary measures to look at our data. Both may summarize study data in a concise and meaningful way if you pick the appropriate data presentation tool. Different types of data require different tools and types of graphical summaries. Here we have the types of data, categorical and interval, and their subtypes, and a loose arrangement of data visualization tools by which type of data they best represent. This is not an exact grouping. We can often use tools across data types, especially when we're comparing different types of data or when we want to look at how data are distributed across multiple variables. But these plots and graphs are the ones that we'll talk about today. Now I'm going to introduce the tools that we often use to present categorical data. The most frequently used data presentation tools for categorical data are frequency tables, bar charts, pie charts, and mosaic plots. I'll cover each of these in more detail over the first part of this topic. As a review, here is an example of a frequency table of reported ethno-linguistic group of household head. It shows the categories of the categorical variable in the first column, the frequency of each category in the second column with the pink circle, the relative frequency or percent in the third column with the green circle, and the cumulative relative frequency in the last column. The cumulative relative frequency is the sum of proportions of the current and previous categories in the table, and hence always equals to 100% for the last category. By now, you should know that to create this table, you can simply type the command tabulate and the variable of interest, here ethnicity. Here is an example of a bar chart. It graphically presents the data from the table on the previous slide on relative frequency of ethno-linguistic group of household head. The categories of the data are presented on the horizontal x-axis, while the relative frequencies are displayed on the vertical y-axis. The height of each bar is proportional to the relative frequency of each category. Therefore, the category with the largest number of observations is the tallest bar on this graph. We may also label each bar by the percent of each category, as shown here. To create a bar chart in Stata with relative frequencies of categorical variables, the easiest way is to use the histogram command. Type histogram and the variable you'd like to chart. Discrete tells Stata it's categorical or not a continuous variable at least. Percent tells Stata you want the relative frequencies or percentages on the y-axis, and you can type frequencies for the counts. Add labels puts labels on the bars, and Y label grid adds grid lines and labels on the y-axis. There are other ways to manipulate the colors, width of the bars, and more, which can be found in the Help menu or the Graph Editing tool. You can also use the command graph bar to create a bar graph. Use the option over and the variable of interest to get bars of each level of that variable. As mentioned, you can change the properties of the graph by using the Graph Editor tool. Anytime you create a graph in Stata, you can right-click on the graph to get a menu from which you can select Start Graph Editor. This will open Graph Editor, where you can right-click on any component of the graph to open the menu of options for that specific component, or you'll find a menu of graph components to the right of the graph that you can choose from. There are also visual schemes or themes you can apply. Try typing the option Scheme Economist with your graph bar command and see what your graph looks like. Here is an example of a pie chart graphically presenting the data from the table on the previous slide on relative frequency of ethno-linguistic group of household head. Pie charts can be good when you're trying to understand the distribution of components of a whole. The categories of the observations are displayed as slices of the pie, with the size of the slice corresponding to the proportion of the whole that category contributes. You can see in the legend how each color represents one of the 5 categories of ethno-linguistic group. You can change the settings for a pie chart in Stata as well by using the Graph Editor or syntax found in the Graph Pie help file. Sometimes it helps a reader visually to see how levels of a variable are part of a whole, as in a pie chart, and sometimes it helps a reader to see a bar chart, which, when reporting relative frequencies, is still parts of a whole. It can appear to be comparing the categories more so than representing them. How do you prefer to see nominal data presented? Can you think of variables in your data that would be better represented by a pie chart or a bar chart? The Stata syntax to create a pie chart is simply graph pie and the option over with the variable in parentheses, just like the graph bar command. To create this pie chart, you can go to the do file for topic 7.5 and run the syntax for this, which is in a theme or scheme that the Economist magazine created. You can use the graph editor to move labels and change characteristics of the chart. What if we want to look at observations by levels of 2 categorical variables at the same time? Let's say we want to look at our ethno-linguistic groups by region of Lao PDR. You should recall from 7.3 that we can create a contingency table to look at variables by levels of another variable. We do this in Stata with the tab or tabulate command, and the variables we want to include in the table with our row variable first. And if you recall from topic 7.3, we can add row, column, and cell percentages using the tabulate command. This gives us the relative frequencies of ethnicity by region. This is a mosaic plot of ethno-linguistic group of head of household by region of Lao PDR. In the past few years, mosaic plots, also called spine plots, Marimekko charts, or Mekko charts, have become more common as a way to display contingency tables, categorical data. These can be a little confusing at first, even though they're quite pretty. If you look at the legend to the right of the plot, you can see that each color represents one of the 5 categories of the categorical variable ethnicity. If you look at the x-axis along the bottom of the chart, you see that there are essentially 3 columns, each corresponding to a region of Lao PDR. The width of the columns is the proportion of the total sample that each region contributes. Along the y-axis, the height of each colored shape corresponds to the proportion of each region that a specific ethno-linguistic group contributes. I'll compare this chart to the frequency table on the next slide to help you see which proportions contribute to which cells. Here, I've put the table and the plot side by side to make it easy to show which parts of the plot represent which proportions in the table. I've taken the legend and put it next to the rows of the table to easily see which ethno-linguistic group matches which color and the row of the table they represent. First, let's look at how the proportions of the region columns correspond to the plot columns. You can see that this total proportion of the sample that resides in the north region is about 38%, and this corresponds to the proportion of the x-axis that the north region column occupies on the plot. Central is about 39%, and the south region is a little more than 22%. Looking now at just the first column for north and at the table column for north region, we can see that of the total sample that resides in the north, 28% is Lao Thai, represented by the blue-gray color block. About 33% is Hmong Khmer, represented by this orange box. About 26% Hmong Mien in the green box. And about 13% Chinese Tibetan, as you can see with the red box. There is no one in the sample that identified as another ethnicity or for whom we have missing data, so there is no blue box in the column for North region. Similarly, you can read the central region column in the table and see how these relative frequencies for ethnicity correspond with the colored boxes in the plot. There is only one red box in the plot in the North region. Chinese Tibetan participants who were in the mixed data all lived in the North. Hmong Mien participants only live in the North and Central regions, but not the South. So not only can we look at this plot and quickly see what the dominant ethno-linguistic groups are in Lao PDR, Lao Thai, and Hmong Khmer based on the sample, we can also quickly see that there are 3 regions of Lao PDR and what the ethnic group composition is of each. It may take a moment to get used to reading mosaic plots, but there's quite a bit of information you can convey when you use them to summarize data. To create a mosaic plot in Stata, you may first need to install the spine plot function by typing ssc install spineplot. Then you type the command spineplot and the variables you'd like to include in the plot. This is the default format for a mosaic plot, but you can further customize your plot with color, font, title, placement of the legend, and you can even change the axis labels if you wanted it to read proportion by region or something else. To do so, right-click on the plot in Stata, and a menu will appear where you can select Start Graph Editor. Then you can right-click on any part of the chart to open a menu to change options. To present interval type of data, we can also use frequency tables. However, we will need to divide the values of the observations into intervals of nearly equal length, given that with continuous data and some discrete data, the table would be too extensive to be useful if reporting the raw numbers. This same approach is used when creating histograms, which are similar to bar charts, but can show frequency distributions for continuous and discrete variables. You create intervals for observations and plot the intervals along the x-axis. Box plots are very useful for showing the central tendency and dispersion of variables, as are stem and leaf plots. Scatter plots, line graphs, and frequency polygons show the distribution of observations for continuous variables. Many of these can also be used to show the relationships between multiple variables. We will need to divide. Histograms are a graphical way to display the frequency distribution for continuous or discrete data that have been divided into intervals. In this case, your software can create default intervals based on your data, unless you have specific intervals that you plan to use instead. In histograms, you plot observations along an x-axis that contains the range of the variable in intervals and a y-axis that is the frequency or relative frequency of observations in each interval. Here's an example of a histogram using the BMI data from the mixed sample. The range on the x-axis is from 9 to 30, and the y-axis here is the percent of the total observations of BMI that each interval represents. Here's an example of data we might plot on a histogram. Imagine we have 50 students who take an exam, and they each have a score on the exam. Each of these scores is in box A, ranging from 61 to 98. To naturally divide the grades into a plus-minus letter scale, where you can have an A+, or an A, or an A-, for example, the professor created intervals of range 3, so from 96 to 98, which would be an A+, 93 to 95, which is an A, and so on. You probably recognize this as a frequency distribution table. So we have our intervals listed, and then columns with the frequency, relative frequency, and cumulative frequency in percent, in order from lowest score to highest for each score interval. We then plot these scores using a histogram, where the score values are on the x-axis and each bar has an interval range of 3, with the plotted value representing the midpoint of the interval. The height of the bar along the y-axis is the frequency of a score interval. What can you see quickly from this histogram? What scores are most common? What scores are infrequent? Can you estimate a central value for these scores? When we look back at the frequency distribution table, we can see that the histogram gives us the same information as the table. The x-axis contains the actual scores, shown in interval bars, with 3 scores per interval. The midpoint of the bar is labeled for the midpoint of the interval. The height of the bar shows the number of times that score appears in the data. The interval with the most observations of scores is the 84 to 86 interval, which you can see is the highest bar. Now, you could make your own histogram by hand if you wanted to, but no need. I'll show you how to do it in Stata. Here is an example of a histogram made in Stata. This is the distribution of valid values of BMI in the mixed sample. Looking at the x-axis, what is the range of BMI in this sample approximately? What is the width of the intervals? What does the y-axis represent in this graph? And how would you describe this distribution? Does it seem normally distributed? What would you estimate are some of the measures of central tendency based on this histogram? We can answer most of these questions about BMI in our sample or make well-informed guesses just by looking at this graph. If we run a summary of BMI in Stata, We can get the values for some of these answers and compare them to the graph. If we look at the graph, we could see, even without the normal curve, that the mode with the most observations was this interval between about 14 and 15. Did you think the mean was a little more than 15? We can see the mean here at the peak of the normal curve. And when we check the summary table, we see it is 15.4. The median is the value right in the middle, and it can be a little harder to determine, but with the shape of this curve, we can expect the median to be pretty close to the mean, and maybe a little less, because it looks like there are more observations to the left of the mean than to the right of the mean. In the table, we can find the median at the 50th percentile, and it's 15.23. The curve has a good normal shape, but like we said, it looks like there are more observations stretching out to the right of the distribution, so it is positively skewed, and our skewness statistic confirms this. In summary, we can get a lot of information from a histogram. You can create histograms in Stata using the histogram command. Using the histogram command histogram and the variable of interest. This will create a default histogram, but it can be customized in menus or with syntax. Reference the do file for topic 7.5 for example syntax. These are histograms of the variable AT10 in the mixed sample, which is hemoglobin in grams per deciliter. Your default histogram will produce a plot with density as the y-axis, as in figure A. You can add the option fraction to the end to get your fraction that each bar contributes to the whole, as in figure B. Figure C is exactly the same as B, but we're labeling the y-axis with percent, and we've added a normal curve with the option normal. Finally, figure D shows the graph with frequency as the y-axis and a normal curve added. If you want to add kernel density estimation to your plot, you can do so by adding the option k-density. Kernel density is essentially a continuous and smoothed version of the histogram. You can see this well on the plot on the left on the line. The default for Stata is to use Epidemiology kernel density, but you can change this using syntax or the menu. You can also plot both the normal density and kernel density on your graph by adding both options of normal and k-density, as in the plot on the right. What else can we learn from histograms? We can look at the characteristics of a single population or variable, as we just did with BMI or hemoglobin in the mixed sample, but we can also compare more than one population, look at how the averages or central tendencies shift in data, and look at changes in variability as well. Here are plots that illustrate a shift in data. These could be the same variable plotted for two different populations, for example, BMI for men and for women, or they could be the same variable among the same people at different time points. For example, hemoglobin measures in one population at time 1 and at a second time point after an intervention. Notice how the shape of the plots are similar, but the bottom plot of dataset B has higher values than the upper plot of dataset A. We can also see differences in the variability of data. The data or variable in dataset A has more concentrated values, while dataset B is more spread out and has observations of many different values. We can understand a lot about the distribution of data when we plot it graphically using histograms. Stem and leaf plots are a neat way to see the frequencies of each value of observations of a variable. This is the default setting for a stem and leaf plot if you use the command stem and then the variable of interest. The stem is made up of each value of BMI except for the last digit of the value, and the leaf contains the final digit of each value of BMI observed in the sample. The shape helps us understand the distribution of the values. So if we look at a BMI of 13, we see the integer of BMI in the stem, and then 5 repeated 9 or 10 times, and 6 repeated 7 times, and so on. That means there are 7 observations or participants with a BMI of 13.6. These can be useful for finding measures of central tendency and getting more detail than in a histogram. A frequency polygon is similar to a line graph of a histogram. This is the frequency polygon for histogram of our exam scores. A dot is placed at each interval midpoint, and then each pair of adjacent dots are connected with a straight line. Here you can see the histogram and frequency polygon for exam scores on one slide. Histograms and frequency polygons provide us with the same information about the data, but the histogram is better for proportions and ungrouped distributions. Frequency polygons are better for grouped distributions for comparing distributions. I'll show you how. Here, we can overlay the distribution of exam scores from two groups onto the same plot for comparison. What can you tell about Group A and Group B from this graph? These 4 plots are all showing the same information on the number of deaths from several lung diseases, but in just slightly different ways. Which of these frequency polygons do you prefer for understanding these data? Box plots are a graphical display of 5 numeric summary measures: the minimum, lower quartile, median, upper quartile, and maximum. They're a good way of visualizing data from different populations, especially when comparing them. It has clear definitions, so you don't have to worry about the number of bars or the class intervals or anything. They're comprised of easily available information, and they could be modified to indicate outliers in your data or extreme values. The basic box plot has the box defined by the lower boundary of the lower quartile or 25th percentile, the upper boundary of the upper quartile or 75th percentile, and the median or 50th percentile in the middle. This means that the box represents the interquartile range, or IQR, and that 50% of the data are in the box. IQR is a very robust measure of variability that can be judged graphically. To the basic box, we add the whiskers, seen here in red, which extend to the adjacent values, labeled here as maximum and minimum, which are the most extreme observations in the dataset that are not more than 1.5 times the height of the box, or the interquartile range, beyond either quartile. When data are fairly symmetric, the adjacent values should cover about 99% of the measurements. Any other points beyond these are called outliers, or data points that are not typical of the rest of the values. Here we have a box plot of the observations collected for BMI in the mixed 2017 10% random sample data. From first look, you can see that the values are fairly concentrated around 15, which we already know is near the median, mode, and mean of the variable. The box representing our interquartile range, or middle 50% of data, is not very tall, meaning that it doesn't contain a wide range of values for BMI. We have quite a few outliers beyond the maximum and minimum adjacent values, or the whiskers of the plot. Let's look at our values for these centrality measures. First, while we can read our summary values along the y-axis, as we did in our histograms, I am bringing back our summary table just so you know exactly where these values are coming from. We have our median at the 50th percentile line, which is 15.23. Our lower quartile, or first quartile, or our 25th percentile, it has many names, is here at the bottom of the box, and the value is 14.25. Then we have our upper quartile, or quartile 3, or 75th percentile, which is at the value of 16.4. We can then know our IQR, or interquartile range. We can also calculate our upper and lower adjacent values, or the whiskers of our box and whisker plot, using the formulas from the previous page, or essentially taking 1.5 times our IQR and adding it to our 75th percentile for the upper adjacent value, and subtracting it from our 25th percentile to get the lower adjacent value. Finally, we have our outliers, or values outside of this range. We know from our summary table what the highest and lowest values are in this variable, and we can easily see where the upper outlying values are at 28.55, 26.36, and so on, and the same for the lower values. The state of command for box plot is graph box, and then the variable you want to plot. The graph on the left, which we viewed in the previous slide, was created using graph box BMI if BMI less than 30. With your mixed sample, run the command graph box on BMI without specifying values, which gives you the box plot on the right. What do you notice? How is it different? The values are much more compressed in the IQR because we see the y-axis ranges all the way to 100 to accommodate our extreme outliers. If you plot your continuous variables when you are first looking at your data, you will very easily be able to identify outlying values that might indicate errors in your data. Box plots are excellent for identifying outliers, and I highly recommend using them early and often. Here we've plotted the values of blood hemoglobin, variable AT10. On the left plot, we have graph box AT10. On the bottom right plot, we've used graph box AT10 if that hemoglobin is less than 17. Again, we can see there are extreme values of 100 that don't make sense for the measurement in our plot of the raw data, so we may want to look at those and recode this variable to not include the extreme values. Or we can do what we did for the plot on the right, which is to plot values only under the most reasonable value for hemoglobin in the sample. In this plot with the valid values, we see that it's fairly symmetrical with only a few outliers. Compare this to the summary statistics for AT10 and to the histogram for the same variable. Box plots are also excellent for comparing distributions of observations across groups or categories. When we plot a continuous variable by a categorical variable, we can easily see how the distribution of the continuous measure differs across levels of the categorical variable. Here we've plotted hemoglobin by males and females in the mixed data. What do these box plots tell you about hemoglobin in men and women in this sample? You can quickly look at how the central measures differ, see whether distributions have different shapes or placement. Does one group have taller or wider boxes, longer or shorter whiskers? Look at the outliers. Are there more in one group than in another? Could outliers in one group be affecting the distribution? Could it be that the range of valid values should actually differ by groups? There is a great deal of information available in box plot comparisons. To create box plots by levels of a categorical variable, we can use the option over and the categorical variable in parentheses. Here is the syntax for plotting hemoglobin levels by sex, which is HL4. We've touched on this a bit already in this presentation, but graphing the relationship between two or more variables is very helpful for gaining a deeper understanding of each variable. There are many ways to manipulate graphs, and there are many additional graphs that we can use, but this will give you a place to begin. When one variable is interval and one is categorical, box plots and scatter plots can be used, as well as frequency polygons or grouped histograms. When both variables are interval data, a scatter plot is most appropriate. We'll cover scatter plots in a moment. When both variables are categorical, you may use grouped bar graphs or frequency polygons, and there are additional options for multiple data combinations. Stacked bar graphs, for example, can show multiple continuous variables by categorical variables. Here's an example of a scatter plot of weight by age. We would expect for weight to increase as age increases. And we can see that there is a positive linear relationship between child's weight in kilograms and age in months. We're also able to fit values to the plot. We can also add a linear fit line to the plot. We'll talk more about creating regression lines and smoothing lines in topic 7.7. But for now, we've used the graph two-way function with a command for a scatter plot, and then on top of it, a command for a linear fitted line. When you combine them, you get a scatter plot with a fitted line. For regular variables with valid values, you can just use the command scatter, and then the two variables you'd like to plot with the y-axis first and the x-axis variable last, no matter how many y variables you have. If you need to restrict values using an if statement, that needs to be done in a two-way scatter command, as seen in this slide. You can use box plots to visualize a continuous variable's distribution across levels of a categorical variable, as we have in this box plot of BMI by region of Lao PDR. The basic syntax for a box plot across a categorical variable is graph box variable 1, which is your continuous variable, over variable 2, which is your categorical variable. You can create bar charts for nominal and ordinal variables that present the relative frequencies of some variable. Here, the level of educational attainment of adults, both by gender and over categories of time. With this, we can compare the levels of educational attainment of men and women in 1968 and in 2000. This is a different kind of grouped bar graph you can create in Stata. The bars represent the means of two continuous variables, weight for age percentile in blue and weight for height percentile in red. These means are then grouped by region of Lao PDR and further split into gender. You can create this with the graph bar command, and here the H bar simply tells it to orient horizontally. Similar to the grouped bar graph in the previous slide, this is a stacked bar graph where the means of the two continuous variables are stacked in each bar rather than in separate bars next to one another. In this graph, we've also labeled the means so that you can see the value of both the weight for age percentile means in blue and the weight for height percentile means in red. This is created using the graph bar command as well, with stack to indicate stacked bars. This is the same graph, but on a horizontal scale. There are many more ways of visualizing data, from as simple as line graphs to mapping geographic data and personal and social network data. But we can't possibly cover them all in one module, but I encourage you to reach out and investigate interesting and compelling ways to display your data that make sense for you and your audience. If you need additional Stata syntax for creating graphs and charts, you can follow the link on this slide to a resource with Stata code. In summary, choosing the best graphical summary for your data depends on the data type. Frequency tables, bar charts, pie charts, mosaic plots are best for categorical data, and frequency tables, histograms, box plots, stem and leaf plots, and scatter plots are best for interval data. There are several types of plots that can be used to show relationships between combinations of continuous and categorical data. And visualizing data in Stata can be completed using syntax and the related do file or through the menu. Final thoughts. You are telling a story through your data, and data visualizations are the images that accompany your story. Whether the audience is only you as you manage your data, or is other scientists or the greater population, use great graphs to make your story compelling.